Throughout this video series trying to explain calculus, we've been focusing exclusively on one half of calculus, namely differential calculus. In this video, I want to actually show the other side of calculus and basically show how that ties in to differential calculus. So basically, with differential calculus, we're trying to find the derivative, which is called can be thought of sort of as the speed. That's sort of what the way Isaac Newton thought about it. He thought about it as the speed at each point in time. But the thing with the derivative is, if we have our distance function that we've been working with, we can use the derivative based on certain rules, and after we learn some basic formulas and some certain rules like the sum rule, product rule, etc. for derivatives, then we can basically derive the velocity function, the derivative of, remember the rate, v equals delta x over delta t, and the derivative is just this sort of concept with smaller and smaller delta t's, to be more accurate over smaller intervals. But anyway, we can use sort of the logic of differential calculus to derive this. And then we can do the same thing for acceleration, because acceleration is defined as the rate of change of velocity over time. And if you do a smaller and smaller interval, you can get a more and more accurate acceleration value at each point in time. And you can keep going too. You can nobody really uses anything above acceleration, but yeah, there are certain concepts. So I think the derivative of acceleration is called the jerk, I believe. So if you take the derivative again, you'd have the jerk, and then the next one is called the snap, and the next one is called the crackle, and the next one is called the pop. If you don't believe me, I'm pretty sure they just named snap, crackle, pop after breakfast cereal, but either way, nobody really cares about anything above acceleration. Modern physics is really built on the concept of acceleration and forces. You really don't need to know the stuff above that, or at least I'm not aware of anything where you would need that. So we're just going to focus on that. And if you think about everything that we've done so far, we basically laid the framework for how to do a derivative, but we're sort of still left with this lingering question. Remember, Isaac Newton, his law of gravity implied that if you drop an object on the surface of the Earth, it will acceleration downward at a constant 9.8 meters per second. So if we draw that here, if the ball's up here, it's the speed is changing 9.8 meters per second per second. If we're down here, it's changing 9.8 meters per second per second. Or I'll say 9.81. This is really an approximation. It does, you remember the law of gravity, it does speed up as it gets closer, but this is such a small distance in proportion to the total radius of the Earth that's really negligible. So we're sort of forgetting about that. Right now it's constant. And remember, the whole point of the laws of physics are to be able to basically figure out how things move, or at least mechanics in the physics, or mechanics in physics. The whole point is to figure out how things move and how kind of energy is conserved. I don't want to get into energy, but that sort of idea. Basically, how objects move. So what we really want to do, we know how to go this way, like basically with derivatives to find to basically find the velocity. If we have a certain function x of t, then we know how to go backwards or go forwards with derivatives to find the velocity, and then we know how to find the acceleration. But we really do not know how to go in reverse. And that's what we want to sort of explore in this video. We want to come up with some way to go in reverse, because think about where we actually are. According to Newton's laws of physics, his law of gravitation, any object on the surface of the Earth has a constant acceleration. So we actually know the acceleration function. The acceleration function is actually just a constant that equals, we'll call it c, where c is equal to, or we'll call it a0. How about that? The initial let's just call it some constant a. Actually, that's confusing. We'll stick with c, because we'll have a for the function and the constant, but it equals some c, where c is equal to 9.881 meters per second per second. And this is experimentally determined based on factors like the mass of the Earth and the radius of the Earth, so on and so forth. So we actually want a way to go backwards. So we're going to think about that. We're going to try to see if we can, think it through and come up with a way to go backwards. So let's do that. Now, we have here, now the first, actually, let me just graph this first. So we actually have here, let's imagine this acceleration as a constant function. So this constant 9.81 meters per second squared. And the idea is, so this is acceleration over time. We want to come up with a velocity graph. So if this is the acceleration over time, what we would like to do, we'd like to come up with some velocity graph. And the question is, what does this look like? We don't really know. So we want to figure that out. How could we do that? Well, and remember, the reason we have to do velocity as an intermediary is because acceleration is really defined in terms of velocity. But what we really want to do is do this step twice, basically. Figure out how to move from acceleration to velocity, and then move from velocity to distance or displacement, like we did before. And if we could do that, then whenever Newton's laws of physics, remember, force equals ma, we can basically add up the forces on anything, on any object, just the instantaneous force, and then we can calculate the acceleration based on that force. And then based on the acceleration, we'll be able to figure out how it actually moves in reality, which is what we really care about. That's the whole point. That's the whole point of this. That's basically why calculus was invented, to solve this problem. Now, it turns out that calculus had a lot of other applications beyond this that really unlocked most of physics in our modern understanding of the world, but this was the first problem that it was invented to solve. So let's think about this. If we think about it in just algebraic terms, the acceleration over an interval is defined as the rate of change of velocity on the interval divided by delta t. Delta v over delta t, the change in velocity divided by the change in time. That's really what we're talking about with the algebraic definition of acceleration. So here's an idea, and for this one, let's actually assume to start that we have some arbitrary function. So a constant function is actually easier to get the logic for, but let's assume that we have some arbitrary function here. Just let's say that's the acceleration. At every point in time, the acceleration changes like this, and our question is, all right, well, what is the velocity graph of that going to be? The idea that we're going to use, it's somewhat similar to the derivative, but in some sense it's the reverse. So in the derivative, basically what we did is we basically had one point. We want to understand the acceleration here. So we basically start at some delta t over here, and we basically calculate the slope, and then we bring the delta t in closer, and then calculate the slope here. Bring it in closer and closer and closer until it gets right up on it, and then that actually approximates the tangent at that point. So that's how we did the derivative. How can we do how can we do the what's going to be called the integral? One thing that we can do, we can rearrange this, because remember, our goal is to find the change in velocity, and the key insight here is to basically break this entire interval into a bunch of small delta t's. So break this into a bunch of small delta t's. So just break it up into a bunch of small intervals, and make an assumption that's incorrect, by the way, but assume that the acceleration is constant on that interval. And if the acceleration is constant on that interval, basically what we'll have is a situation where we add up all the tiny delta v's on the interval, and we're going to assume those are equal to the a on the interval times the amount of time. So in other words, we're going to assume that the acceleration is going to be, instead of having a function like this that's curved and continuously varying, we're going to assume we have a choppy function, basically like this. So we have accelerate for delta t. Let's say delta t is like 0.1 seconds. Let's say we're accelerating at this speed, and then we instantaneously jump up and accelerate at this speed for a little bit, and instantaneously jump up and accelerate at this speed. Continuing to do this, you get the idea. Now, sometimes we're going to overshoot it, sometimes we're going to undershoot it, um, but it's going to be decent. So like you can see here, you can see we're undershooting. If we use this approximation method, we're basically undershooting the function by a little bit. And you can see that we're overshooting it by a little bit here. And then we go back to undershooting it. Overall, a lot of this is going to cancel out, but it's not going to be exact. So this is really an approximation at this point. So we should probably mention that. We should mention that it's an approximation. So this is only a decent approximation. So if we do that here, though, now you can think of this a over the interval as basically this point here, which is why it's constant. So if we take this a and multiply it by a delta t, if we do that for the first one, so let me actually list this out. So to actually list these out, we would basically have a of 0 times delta t plus a1 delta t plus a2 delta t dot 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 for as many as we have in the interval. And if you're actually actually I'm going to leave them in. I could distribute this out, but I'm going to leave it in actually for now. But if you think about this, well, what's a of 0? A of 0 is the value right here at the beginning of this interval. So if we have a of times delta t, you can actually think of this as a small rectangle, which has a width of delta t and a height of a of 0. So that's what this chunk represents. So it actually represents this first chunk here. That's one way to think about it. We're just using the definition of acceleration to actually come up with this approximation, but it actually does have a geometric interpretation, and that's basically the area under the curve, or an approximation of it. This a1, well, that's going to be this value here, a1, and same situation. We're looking at a1 times delta t. That's another rectangle. That's the one right here. So that's this sliver right here that we're talking about. So that's this value. So we cover these two. And then, the second one here, blah, blah, blah. Point is, if you take all these areas, obviously, geometrically, doesn't that sort of look like a pretty close approximation to the area under the curve? Yeah. So that's the basic idea. The basic idea is, we take a small step, see how fast we were going, and then do another small step, see how fast we're going, and just add up all those steps. And if you add all the steps, then you'll end up with the total. You'll end up basically with the distance covered over time. Now, so that's kind of a handful to take in. That's the basic idea of the derivative, or sorry, the integral. But it's not actually precise enough because, we have these errors here. So how can we make it more precise? Well, in the same way that when we're taking the derivative, we basically shrunk delta t to change the slope until the slope closely approximated the tangent. What we can do here is we can shrink delta t, which really consists of taking more intervals that are smaller to get more approximations to the area under the curve. So, for example, instead of let me just do some basic whoops, let me do some basic redrawing here. If we get rid of, or actually I'm not able to do that, but anyway, let's say for the following ones, instead of taking delta t, we cut delta t into 10. So if we took, or let's say 5, or as many as I can draw. So these are the new intervals. They're going to be a lot smaller. So this is what happens as delta t approaches 0. We're taking a bunch of smaller and smaller intervals. Because the intervals are smaller and smaller, the values are actually closer to what they are on the curve at that point in time. And you can kind of see how we're really not overshooting a lot anymore. So before, when we were overshooting or undershooting by quite a bit, now we're basically exact. Not literally exact, but basically exact. And the idea is, as we take the limit, as we take more and more of these partitions, as delta t approaches 0, delta t, remember, is the width of the partition, it's going to basically close in the exact area under the curve in the limit. So that's the idea. That's the basic idea. And we can actually describe that. And basically, so you might be asking, okay, so how does this area under the curve correspond to the velocity function? Well, basically, it would be the accumulated area. So, for example, if we look at this, that would maybe correspond to a velocity like this. And then we add more area, well, velocity goes up. And then we add more area, velocity keeps going up. We add more area, velocity keeps going up, and now we add more area, velocity keeps going up, but it goes up slowly. It goes up more slowly, and now, basically, as we add more area, adding more area corresponds to the velocity getting higher, or at least that's one geometric interpretation. But you don't even have to think of the geometry involved. Actually, you can just think of the logic. The logic actually makes more sense, in my opinion, than the geometry. Um, Basically, you're taking very small steps, taking a sample of the acceleration at that point, and then multiplying it by the width of the partition. So basically, you can think of it, if you're, one way to think about it is if you're sort of in your car. Let's say you're in your car, and your car is going smoothly. So we have your car, and then there's your car. It's the road. You're sort of smoothly stepping on the gas to accelerate. So let's say your acceleration actually looks like this. If we graph the acceleration over time, one way you could look at it is you hit the gas, move a little bit. So you move a little bit, delta t, accelerate a little bit, and let off the gas, and then step on the gas again at a new value. Do another small step, another small step, another small step, and if you just if you know how fast you're accelerating at each one of these little steps, and you add them all up, well, acceleration at each step equals delta v at that step divided by delta t. So if you just add those up, then you'll be basically each time you'll be adding a delta t, which crosses out, so you actually know the velocity at that step. So that might be a little bit too vague, but that's at least the principle of what's going on. So if you wanna like think about what we're talking about here, what we're really talking about as we approximate the area under some curve, we're actually with a bunch of partitions. What we're really talking about is this. So the integral, in by the way, I should add that this only makes sense on some interval between x and, or between t equals, it only makes sense at some start time and end time. So you have to have some, t equals a is usually the start, and t equals b. It's only defined on a certain interval because you have to have the actual beginning and end of an interval defined before you can actually split the internals into different partitions. Like you have to know that. You have to know where to stop. We're not taking any partitions outside of this range. We're just doing it inside. So the integral symbol is used. This is the integral symbol here, right? Actually, it's supposed to be a big S for sum. If you remember back the sigma notation where you basically add a bunch of terms, it's sort of like that, except you're adding an infinite number of terms if you want to think of it that way. That's sort of why this is a big elongated S. So we do that. And let's say this is some function called the acceleration. Say the integral, actually this whole thing is equal to the velocity function. It's equal to the integral of the acceleration times little t. This is basically the symbol in the same way, for the same way that when you have a derivative, before when we were talking about the derivatives and we did the prime, or we did dx over dt, and then we say that's the derivative. This is that for the integral. That's basically what this is. It's just the way that the integral is represented. But the way that the integral is actually defined is the following way: limit of n limit as n approaches infinity, not 0, of the sum from I equals 1 to n of a, I'll call that I, a of t, I, and then we'll take the sample. So that's what this means. It's a sample point. And we'll do that over delta t, where delta t is defined as b minus a over n. So if you think about what, you might not be, this might be pretty confusing. So we just need to think about what it means. What we're talking about here, so this a, or actually I should probably define this before I start. So a equal a of t, this star here is sample sample point in ith partition. So for example, we have some graph here, some arbitrary function, start at A, and basically the delta t is going to be obviously b minus a, the entire interval divided by how many intervals we want to do. That's what n is. So let's say we were doing 3 intervals. Let's say n is 3. So obviously that'll be 1. I didn't draw it well, but yeah, let's actually let me redraw it a little bit. Just redrawing it. These are the 3 intervals. Still not very good. They're supposed to be equal, but that's delta t. Every one of them is delta t. And here we're doing n equals 3. And this a to the I, so like this will be the first partition. Partition 1, partition 2, partition 3. And this a to the I is really any sample point in between here. So between this number and this number, you can choose any one of them. The reason you can choose any one is because as we let n go to infinity and we get finer and finer partitions that shrink, then you'll sort of be forced to one value. So you can really pick any one. Usually when you're calculating, you usually pick the left or the right. The right's actually a little bit easier, so maybe we'll pick this value for that. So we'll say that's the value, and then we're going to multiply that by delta t. So the first one, let's say this is, I don't know, say that's 4. And then we'll say this next one for the second partition is 3.5. And then this last one for this last partition we'll say is 6. So the way that this would be listed out with n equals 3 is that we have basically, or actually I'm not going to do the summation. I'll just write out the actual terms themselves. So basically A1, or A1, which we're going to say is, actually I won't even do that. I'll write this out. Actually, no, I will. I'll do A1 times delta t plus A2 times delta t plus A3 times delta t. That's what we're talking about when we say this. So, and we're going to say, let's say delta t, let's say this whole period, let's say this whole, let's say that b is 8 and a is 3. Actually, let's just say that b is 6. Say that b is 6. So that n is 3, and that would mean that delta t, using this definition here, delta t is really just the width of a partition based on a certain number of partitions. It really makes sense. It's just sort of basic. So 3 minus 6 minus 3 is 3 divided by 3. So we're talking about delta t equals 1 here. So each one of these is basically going to be 1 wide. That's basically what we're assuming. So we're basically going to have 4 times 1 plus 3.5 times 1 plus 6 times 1. And this will actually pretty approximate the area under the curve. It'll basically be this. So it'll be a decent approximation. Anyway, just imagine instead of having n equals 3, we had 1,000. So delta t would get a lot smaller. It wouldn't be 1 anymore. It'd be like 0.001. And the values, the sample points, would be much closer to the actual value at that function, or value of the function at that point in time, delta t. So that's what this is trying to represent. It's like instead of saying n equals 3, we're saying, okay, we know how to calculate this sum. This is a way to calculate it for n equals 3. Our approximation will get better if n equals 4. If n equals 5, it'll get better. It'll get better and better if we let n increase to infinity. So think about what this would be if n is 10,000 or 10 million. We'd have 10 million different partitions, each very small, very, very small slivers of rectangles, and the error would constantly be decreased. Like we wouldn't have this overshoot here. So if you think of this here, that I'm shading dark now, that's actually an overshoot. The function is here, but our approximation is way up. As we let n go to infinity, these overshoots are going to basically decrease to 0. They're never going to hit 0 exactly, but in the limit, there's that word again, the limit. That's the whole point of calculus. Everything in calculus is just limits. In the limit, it'll approximate 0. And they'll tend towards 0, and you'll get a better and better approximation If you actually try to calculate this with n equals 10,000, you know, that's what you would get. So that's the basic idea of the derivative. I just wanted to sort of explain how we actually solve it, but this actually does give us a way to move between the acceleration and the velocity. So in the next video, I'm actually going to try to derive, I'm actually going to try to go backwards and derive some basic functions using some maybe simple acceleration functions. We're going to try to go backwards and get to the velocity and basically do the opposite of what we did with differentiation. So stay tuned for that.